50 multiple-choice questions, 9 chapters of foundational chemistry. You will have your reference tables, so this exam does not test rote memorization. It tests how rapidly you can apply laws and formulas under time pressure. This roadmap outlines your strategy. Success depends entirely on your fluency across 4 operational pillars: foundations, stoichiometry, bonding, and gas laws. On screen, we see the metric prefixes table alongside the states of matter transition diagram. Absolute precision with these conversions and phase changes forms the baseline for every advanced calculation on the exam. You must execute atomic notation flawlessly. That requires rapidly calculating the exact number of protons, neutrons, and electrons for any given isotope or ion. Looking at these tables for polyatomic ions and transition metal charges, you are expected to translate complex chemical names directly into exact formulas, accurately accounting for variable charges. If you stumble on this basic inorganic nomenclature, your ability to balance chemical equations in later chapters stops immediately. To bridge the gap between individual microscopic particles and macroscopic measurable mass in the lab, you must rely entirely on the mole. This flowchart maps the core conversions. You will use Avogadro's number and molar mass to execute mole to mole, mass to volume, limiting reactant, and percent composition calculations. Those base calculations are then required to derive specific empirical and molecular formulas from raw mass or percentage data. Look at this sample calculation for sucrose. Fluency in these exact molar mass operations is the only way you will clear practical dilution and yield problems before the clock runs out. Here we have the 1s to 6s orbital energy diagram displayed next to a 3D periodic table. Understanding this electron filling order allows you to directly predict physical periodic trends, like a decreasing atomic radius. This 3D electronegativity chart charts the variation of values across groups and periods. The numerical difference in these values dictates whether a specific bond will act as nonpolar, polar covalent, or ionic. This chart displays linear and trigonal planar geometries. You start by using valence electrons to build 2D Lewis structures, which then dictate these 3D VSEPR configurations. Moving to the tetrahedral parent structures table, observe how unshared electron pairs force the geometry into complex variations, like bent or trigonal pyramidal shapes. An atom's electron behavior strictly governs both the geometric shape and the reactive physical properties of every molecule. Gas behavior follows strict proportional relationships. The ideal gas equation, PV equals nRT, operates above a hard baseline of absolute zero. Notice how pressure, volume, and temperature variables shift. You must integrate Boyle's, Charles, and Dalton's laws into one system. To execute calculations like this nitrogen gas problem without failing, apply one strict rule. Always convert your temperature to Kelvin and explicitly align your pressure units with the chosen ideal gas constant to ensure accurate unit cancellation. If you spend exam time hunting your reference tables for a polyatomic ion or an electronegativity rule, you will run out of time. Abandon passive reading. Actively drill the specific example exercises listed in the study guide and use the previous guides from exams 1 through 3 to patch any remaining gaps before test day.